Okay, so let's get started with a continuation of our lecture on cyclic conformations and conformations of primarily cyclohexane ring systems. So when we last left off, we proceeded through a series of conformational analysis problems looking at the highest and lowest energy chair conformation of cyclohexane ring systems. However, the two chair conformations which we discussed are not the only possible conformations of cyclohexane, but instead these are typically the lowest energy conformations. To remind everyone as to why the chair conformation is the lowest energy conformation, we have to first look at this idea of torsional strain. As we discussed, if we compare our hydrogens on adjacent carbons, these hydrogens are staggered. And because all of our hydrogens on adjacent carbons are staggered, the torsional strain is minimized for our chair conformations of cyclohexane. Now, in order to interconvert between chair conformations, we have to undergo a process known as a ring flip. Okay, and in order to complete this ring flip, our cyclohexane is going to go through a series of intermediate conformations. So first and foremost, when cyclohexane undergoes a ring flip, first and foremost, one of our carbons is going to move up. So the carbon that's pointing down, which is we're going to arbitrarily label as carbon number 4, moves up slightly. So now you have a large number of carbons in a flat plane with one carbon pointing up above the plane. We'll label this as carbon number 1. This conformation is known as the half-chair conformation. The half-chair conformation is particularly high in energy, and one way that we can help visualize why this half-chair conformation is so high in energy is let's look and let's try to examine the relative position of our hydrogens in this half-chair conformation. So one of the key features of the half-chair conformation is our hydrogens on adjacent carbons are eclipsed. And as a result, you end up with this extremely large torsional strain. Now, of course, there are two varieties of half-chair. So for example, in the rightmost cyclohexane ring, we move our bottom carbon up, and now it's right here. And again, we still have these similar eclipsing interactions that are particularly destabilizing. We have gone from a completely staggered system to a system with a range of eclipsing torsional interactions. The half-chair conformation is very high energy. It's about 44 kilojoules per mole higher in energy. Just to give you a sense of where this is coming from, just to recall, a hydrogen-hydrogen eclipsing interaction is approximately 4 kilojoules. So if we count up each of our interactions, we can get a sense of just about how many of these eclipsing interactions we have. So I count 1, 2, 3, 4, 5, 6, 7, 8. So we have at least approximately 8 hydrogen-hydrogen eclipsing interactions, which we would expect to cost us about 32 kilojoules. If we continue to draw out our hydrogens on this uppermost carbon, they're not quite eclipsed in this uppermost carbon, but one other thing that we need to consider is that when we distort the relative positions of our carbons, we also begin to introduce some angle strain. We are distorting our carbon-carbon bond angles from their preferred bond angle of 109.5 to either, for some carbons, a little bit greater than 109.5, and for other carbons, a little bit less than 109.5. Okay, so that gives us a sense of where this 44 kilojoules per mole is coming from here. And the key thing I want you to recognize, the half chair, we have a bunch of hydrogens completely eclipsed, and as a result, it's relatively high in energy. Okay, now from the half chair conformation, we can adopt what's known as a twist boat conformation. Now, the way that this works is if we think about what we want to accomplish in a ring flip, as we discussed, carbon number 4 is going to be moving up and carbon number 1 is going to be moving down. Okay, so we've done the first step to generate our half chair where carbon number 4 was raised up. Okay, now in order to go from our half chair to our twist boat, we are going to take carbon number 4 and we are going to further raise it up. Okay, so we're going to push carbon number 4 up, and as a result, we end up with the twist boat conformation. Okay, so let's label our carbons 1, 2, 3, 4. So now carbon number 4 is up, carbon number 1 is up. Perfect. This conformation is known as the twist boat conformation, and one of the real benefits of the twist boat conformation is seen by looking at these uppermost hydrogens. So these are known as quote unquote flagpole hydrogens, and in the twist boat conformation, the reason why this twist is so beneficial from an energetic perspective is we have separated our flagpole hydrogens. And we've minimized this steric interaction. If these flagpole substituents were brought closer together, we don't have to pay a bit of an energetic penalty as these substituents are bumping into each other and experiencing a steric interaction. Additionally, really critically, if we look at our hydrogens, we notice that as a result of these twists, these hydrogens are not fully eclipsed. So as a result, although the twist boat conformation does experience a little bit of angle strain, we are distorting our bond angles. We are paying a bit of a penalty. We have minimized some steric strain. So really just to showcase, to help showcase this idea, we have minimized our potential steric strain from our flagpole substituents. We have minimized as well our torsional strain, because these hydrogens, if we compare these hydrogens to the adjacent hydrogens, they're not fully eclipsed. And this is really easy to see in the model picture right over here. As you notice, if we compare these hydrogens on adjacent carbons, these are somewhat staggered. So they aren't fully eclipsed. Likewise, if we compare these two hydrogens, they are not fully eclipsed. So we do pay a little bit of penalties. This is the energy of a twist boat cyclohexane relative to a chair conformation is about 23 kilojoules per mole higher in energy. There are some torsional interactions, and you definitely experience some penalties as a result of angular strain, but overall the twist boat is relatively not that high in energy. Now, continuing on from our twist boat conformation, so just to label our carbons once again, 1, 2, 3, 4, 5, 6. So our end goal is for carbon number 1 to be brought down. Okay, now in order to complete this ring flip, instead of just immediately bringing carbon number 1 down, we're instead going to go from a twist boat conformation to a boat conformation. And the way this is accomplished is by bringing carbon number 3 up and carbon number 5 down. Okay, so with that established, so carbon number 5 is going down, carbon number 3 is going up, and we end up with the boat conformation. The boat conformation is higher in energy than the twist boat conformation. And this is readily apparent if we pay attention to our flagpole substituents. If we look at these two flagpole substituents, we are experiencing a substantial steric interaction. We are bringing two substituents that take up space very close together in three-dimensional space. And this repulsive interaction raises the energy of our system. Further, we have introduced a pretty unfortunate set of eclipsing interactions. So if we compare the hydrogens on our adjacent carbons, these hydrogens are eclipsed. Again, one thing I always want you to take away from this is that strictly planar carbons will inherently have eclipsing interactions in most cases, and that's very destabilizing. These eclipsing interactions introduce a large amount of torsional strain. So the twist boat is relatively high in energy. Now, the boat conformation is higher in energy than the twist boat conformation. Now, to help you visualize a little bit how to perform a ring flip and what substituents are moving during a ring flip, let's take a look at the full process. So we've gone from chair to half chair to twist boat to boat, and then we'd continue along this process going through another, which in many cases is energetically similar, but not quite identical. If the substituents are different, we'd go through another twist boat, another half chair, and finally return to our second chair conformation. So let's start to visualize the various conformations in an energetic diagram. So our lowest energy conformations are chair conformations. Now, after we bring up carbon number 4, we end up with our highest energy conformation, which is the half chair. And the reason why the half chair is so high in energy is that it experiences a relatively large amount of torsional strain. Now, once we, so 1, 2, 3, 4. Okay. Now from here, as we discussed, to go from the half chair to the twist boat conformation, we are going to continue to bring carbon number 4 up. So we have 1, 2, 3, 4. Oops, let me draw this perspective a little bit more clear. 1, 2, 3, 4. Okay, and again, now that we have the twist boat conformation, it's relatively low in energy because we've minimized these flagpole interactions and we've minimized torsional strain. Now, after moving carbon number 3 up and carbon number 5 down, we end up with our boat conformation, which is higher in energy than the twist boat because we have these flagpole interactions as well as a large amount of torsional strain as a result of our hydrogens being eclipsed. Now, continuing on from here, if we want to complete the ring flip process, so keeping our carbon numbering, we're going to move up carbon number 6, and we're going to move, so we moved carbon number 6 up, and then we're also going to move, let's see, so we move up carbon number 6, definitely that works, and then we're going to move up carbon number 3 as well. So then filling in, so numbering our carbons, once again, we have the following twist boat. Now, one thing I do want you to appreciate is although these twist boat conformations are similar in energy in this case, the energy will depend on substituent interactions. There are certain cyclohexane systems that may prefer twist boat conformations or may prefer a conformation that is not quite a chair conformation depending on their interactions of their substituents. Further, if you have a substituent such as a methyl on your cyclohexane, that changes the energies of all of these torsional and steric interactions, and as a result, your two twist boat conformations and your two chair conformations, as we've already seen, may be different in energy. So this is a relatively simplified system, but what I want you to appreciate is taking a look at each of these conformations and, just like before, analyzing their torsional interactions and their steric interactions. Okay, so continuing on with our conformational analysis and continuing on with completing our ring flip. So to access our next half chair, we are going to bring carbon number 1 down. We're going to bring carbon number 1 down. And so now carbon number 4 is the carbon that's pointing up above the plane. To complete our ring flip process, we're going to bring carbon number 1 down once again. And now we have carbon number 1 here and carbon number 4 here. One moment. Let's just check, since these Yep, perfect. Okay, so this is the complete energetic diagram for a ring flip for a cyclohexane system. And we're going to look at a few examples where, depending on the substituents, the relative energy of each of these intermediate cyclohexane conformations will change. So let's try to do some studies on ring flips, and let's look at some common mistakes that are often encountered when students perform a ring flip. So one common mistake that I see a lot of students make is they do the chair flip and they forget to invert the positions of their hydrogens. So just make sure when you undergo a ring flip, all of your axial substituents will now end up in the equatorial positions. Now, one other common issue I see, so let's just think about the ring flip for a moment. So labeling this as carbon 1 and this is carbon 4. Carbon 1 is going to move down, carbon 4 is going to move up. So now carbon number 4 ends up at this position, and carbon number 1 ends up at this position. Or it should end up at this position. Now, the issue with this structure drawn is that if we look at this methyl substituent, it is up. It's in the up position, right? So it's axial up. After a ring flip, the methyl substituent should still be in the up position. Now, if we notice in the current drawing, so in the current drawing that we have, it is equatorial, but it is not up, it is down. So if we were to help us visualize this, we have drawn in the first structure, in the first conformation, something that looks like this. In the second structure, we have drawn our methyl pointing down instead of up. So we've in effect drawn a mirror image of our initial structure. This is known as an enantiomer. So really be careful that you don't accidentally draw an enantiomer and that the relative stereochemistry of your substituents stays the same. So if we were to draw this correctly, we would draw it like so. In this case, the methyl, in this case, our methyl group is in the equatorial position, but it is pointing up. It's also really important, and the reason why I always like to number my carbons is that you really don't want to accidentally move substituents around. You don't want to move substituents to different carbons haphazardly, or you'll end up potentially drawing an enantiomer, or even worse, drawing a constitutional isomer. So let's look at another example. So this is really important. Ring flips do not change your stereochemistry. It only changes whether your substituent is axial or equatorial in your ring. So for example, in this case, we have a methyl group that is axial, pointing up. So if we were to draw out using dash wedge notation, this methyl group is pointing up. After a ring flip, so carbon number 1 is here, carbon number 4 is here, carbon number 1 goes down, carbon number 4 goes up. Okay, so we have carbon number 1 and carbon number 4. Perfect. And so we expect after a ring flip to go from axial to equatorial. So our correct structure would have the methyl group at the equatorial position. And again, really critically, this is equatorial, and the methyl group is pointing up relative to the hydrogen. So we have the exact same stereochemistry. We have not accidentally drawn an enantiomer in this correct structure, but we have successfully undergone a ring flip and changed this methyl from axial up to equatorial up. And this is really important because depending on the relative energies of these conformations, one of these conformations may be more accessible under normal conditions, and as a result, that influences how these cyclohexane rings can react, especially if reactions require a certain relative position of substituents. Okay, so just make sure you are really careful with your cyclohexane ring flips. So let's now look at an example of some polycyclic molecules. Polycyclic molecules, so 2 or more rings fused together. A classic example is the decalin ring system. It's 2 cyclohexane rings joined together to share bridgehead carbons of carbon 1 and 6. Okay, there are 2 isomeric forms of decalin, transfused or cis-fused. So in cis-decalin, our hydrogens are on the same face. In trans-decalin, the hydrogens are on opposite faces. Okay, so in this case, both these hydrogens are pointing up. In this first case, this hydrogen is axial pointing up. In the second case, it's equatorial. Okay, so we're still following the typical rules for our cyclohexane ring systems. And if we compare this to our trans-decalin, we have a hydrogen that is axial pointing up, and the second hydrogen on our bridgehead is axial pointing down. Okay, now, it may not be readily apparent, but just like any of our normal cyclohexane systems, decalin systems can also undergo a ring flip. Now, these ring flips are not converting between cis and trans. And one interesting feature, if we compare cis-decalin and trans-decalin, is that trans-decalin cannot ring flip. Now, you can try this with a model kit, but suppose that you did want to ring flip decalin. We need to bring carbon number 1 down and carbon number 4 up. Now, if you try to do that, if you try to actually execute on this ring flip, you'd quickly notice that no matter how hard you try, there's no way to easily bring this axial hydrogen into the equatorial position. Transdecalin cannot undergo a ring flip because if you attempt to ring flip transdecalin, you'd introduce so much strain that it's just not allowed. So trying to bring this axial hydrogen into the equatorial position just doesn't work. It's too high in energy of a ring flip. Now, looking at cisdecalin, we can actually study it just from the same perspective that we have always looking at ring flips. So in this case, let's look at our ring flip for cisdecalin. So let's look at one of our cyclohexane rings. And in this case, we're going to look at the cyclohexane ring in blue. And let's ring flip this cyclohexane ring. So carbon number 1 is going to move up. Carbon number 4 is going to move down. Let's check just to make sure that we have the relative positions. Okay. So when this decalin ring undergoes a ring flip, what we're also going to do, just to check the relative positions. So let's look at the stereochemistry of this hydrogen on carbon 1. So first things first, it starts off in the axial up. It's in the axial position with a stereochemistry pointing up. And at the end of our ring flip, it's in the equatorial position, also pointing up. Likewise, the second hydrogen is in the equatorial position, pointing up. At the end of the ring flip, it's converted to the axial position, also pointing up. So we've preserved our stereochemistry after the ring flip. Now, one thing that I do want you to pay a little bit of attention to, as well, is that this ring flip occurs for both of our cyclohexane rings, and all of our substituents that were originally in the axial position are now in the equatorial position. So for example, let's pay attention to carbon number 9. So we have this axial substituent that's pointing up. After the ring flip, if we zoom in on carbon number 9, that axial substituent is now in the equatorial position, pointing up. So both of the rings are flipped when decalin undergoes a ring flip. So that's something that's unique about the decalin system. But again, always make sure to use your stereochemistry as a guide. As long as you're making sure that your stereochemistry is preserved, you won't run into any issues. You won't be asked to analyze in detail these complicated bicyclic systems, but it's really important to show that we can apply the same method of cyclohexane conformational analysis to more complex systems. Okay, so with that, we're going to now delve into chapter 5, which really focuses on this idea of stereochemistry that we brought up and we're going to now develop further in this chapter. So just as an overview, let's do a little bit of a refresher on constitutional isomers. So constitutional isomers, we have the same molecular formula with a different connectivity of atoms. So for example, we have moved our alcohol from carbon number 2 to carbon number 1. Formula is the same, number of atoms is the same, but we just have a different connectivity. Now, stereoisomers have the same connectivity of atoms, but they have a different 3D and spatial arrangement of atoms. So we've actually seen stereoisomers before in the context of alkenes. So we have the cis stereoisomer, which has the substituents on the same side of the alkene, while with the trans isomer, the substituents are on the opposite side of the alkene. These two molecules have different 3D shapes. We have a different stereochemistry looking at our alkene. Additionally, when we looked at cyclohexane systems, we've also observed cis-trans isomers, which are stereoisomers. So for our cis stereoisomer, the substituents are on the same face of the ring. For example, both of our methyl groups are pointing up. Comparatively, when we look at our trans stereoisomer, the substituents are on opposite faces of the ring. So both of our one methyl is pointing up, the other methyl is pointing down. So the key thing is we're looking at the relative arrangement of substituents in 3D space. And if we have a different three-dimensional shape and the same connectivity, we're dealing with stereoisomers. So let's think a little bit about chirality. And when you want to think about chiral molecules, chiral is based on this idea of handedness, where you have two species, two molecules that are non-superimposable mirror images. No matter how hard you try, no matter how much you rotate, you will never be able to perfectly superimpose the mirror images. So if you take your hands, for example, and try to bring your hands on top of each other, even though your left and right hand look very similar, no matter how hard you try by rotation, they'll never exactly match. They have a different relative arrangement. Your fingers are arranged differently in 3D space on each hand, and no matter how hard you try to bring them and overlay them, they'll never be a perfect imposable set of mirror images. They're non-superimposable. So to use a more chemical example, if we compare these two enantiomers of amphetamine, we can see that no matter how hard you rotate, if you try to bring these two molecules on top of each other, you notice that in the structure on the left, the hydrogen is on the right, and on the structure on the right, the hydrogen is on the left. So our substituents have a different relative position, and because all of our substituents are different, these two mirror images cannot be superimposed. So many organic molecules have non-superimposable mirror images that results from substitution patterns on an sp3 hybridized carbon. So chiral molecules contain non-superimposable mirror images. Another term that we can use is we can say that they lack an axis of symmetry. Now, enantiomers, it describes a very specific set of molecules. It's a pair of molecules that are non-superimposable mirror images. So for example, let's look at the following pair of molecules. So we have a total of 4 unique substituents. And as you're following along, I'd highly encourage you to build a model of each of these two structures. So just as a reminder to help everyone read dash wedge notation, so the way that you transcribe dash wedge notation is I draw my flat plane of the page. So all of our straight lines are just in the plane of the page. So our bromine is flat in the plane of the page. The chlorine is flat in the plane of the page. And now what we're going to do is we're going to look a little bit at how we process dash and wedge stereochemistry. So this wedge stereochemistry tells us it's pointing out of the page. It's pointing out or up out of the plane of the page. So this fluorine is pointing out towards me. Okay? And the dash notation, this dash notation tells us it's pointing in or down further into the plane of the page. This hydrogen is pointing into the page away from me. Okay, perfect. So with that established, let's now transcribe this second structure. Let's try to visualize this second structure and let's see what's going on there. So we have our bromine and we have our chlorine that are in the plane of the page. Perfect. We now have our fluorine, which is pointing out of the plane of the page, and our hydrogen, which has the dash notation, is pointing into the plane of the page. Okay. So in terms of transcribing each of these structures, let's now try to draw some 3D pictures. Let's try to draw some 3D pictures. And if you're playing with your model kits at this time, now would be a good time to start rotating your model kits. And our goal in this exercise is to try to look at these two structures, and we're going to try to rotate them to see if we can find an identical structure. Now, we'll focus more on the mechanics of how rotation works, but for now, I just want you to think that anytime you have a set of 3 substituents, so 1, 2, 3, you can exchange their positions by rotating either clockwise or counterclockwise. Okay, so with that premise in mind, we're going to now draw out some 3D pictures of each of these molecules, and we're going to play a game where we rotate each of these molecules and try to match them up. So, first things first, let's start with our molecule on the left. Let's start with our enantiomer on the left. So I'm going to draw my bromine on top. Let's use a different color for chlorine. My chlorine is going to be in the plane of the page on the left-hand side. The fluorine is pointing out, and the hydrogen is pointing in the back. Okay, perfect. Now let's draw out a picture for the enantiomer on the right. Okay, so for the enantiomer on the right, so we have our bromine on top. Let's use the same color for bromine. We have the fluorine pointing out on the left-hand side. The hydrogen pointing into the plane of the page on the left-hand side. And finally, we have our chlorine on the right. Okay, perfect. So now that we have our substituents all in place, our goal now is to rotate this molecule and to try and overlay these molecules to show that they are non-superimposable. Now, the way that one way to help us visualize this is that we can rotate any set of 3 substituents. We can rotate them either clockwise or counterclockwise to change their relative position. So what we're going to do is we're going to take our substituents and we're going to rotate our substituents in a clockwise pattern. So after rotation in a clockwise pattern, essentially what we're doing in this case is we are changing our view, we're changing our viewpoint so that we're looking at it from the same perspective as our enantiomer on the left. So if we rotate our substituents clockwise, we'll end up with the following structure. So our bromine is not being rotated, it's still on top. Okay? Our chlorine is now going to be, as it's rotated clockwise, it's now going to be on the left-hand side. Our hydrogen is now going to be pointing up towards us out of the plane of the page. And our fluorine is going to be pointing into the plane of the page. So these two structures are identical, and we've only just rotated our bottom three substituents clockwise, just like turning a steering wheel. And from this, we can very easily see that if we try to overlay our two enantiomers, our substituents are different and they're in different positions. So these two species, the structure that we have drawn on the left and the structure that we have drawn on the right, are enantiomers. They're non-superimposable mirror images. When overlaid, our substituents are in different relative positions. And if you'd like to play with a model kit further, we can even show this idea of enantiomers looking at this pair of simplified molecules below. So just like before, if we want to get our green substituent in the same position, we'd have to rotate this molecule counterclockwise. So we have our carbon in the middle. Our substituent X on top doesn't change in position. Our green hydrogen is now on the left-hand side. Our blue substituent is in front. And our yellow substituent is in the back. And no matter how hard we try, if we try to overlay our two enantiomers, as we can see, our substituents are in different relative positions in these two structures. They are non-superimposable mirror images. Now, we're going to focus on developing the skill of rotating and visualizing molecules in three-dimensional space, but I really do encourage you to break out your model kits as just physically manipulating your model kits so that the structures have the structures can be overlaid, and just comparing your two molecular models is really invaluable for this chapter in particular. Let's now continue on and let's talk a little bit about how we can analyze molecules to determine chirality based on this idea of an axis of symmetry or looking at the substituents attached to each carbon. So a chirality center is a carbon with 4 different substituents. And a chirality center is also known as a chiral center, stereocenter, stereogenic center, or asymmetric center. So a more straightforward definition is that a molecule that contains chiral centers with no axis of symmetry is considered a chiral molecule. Now, it's really important that you build models in this case, because once you have your model kits in hand, it becomes quite easy to see why you need 4 different substituents. So let's take a look at this CH3X. Now, if we look at the 2 mirror images and we try to overlay these 2 structures, looking at these 2 structures, are they exactly identical in terms of the relative position? So do we have a hydrogen on the left? Yep, we do. Do we have a hydrogen in the front? Yes, we do. And a hydrogen in the back? Yes, we do. So because we have 3 identical substituents, the mirror image is exactly identical. Let's look at a case where we have 2 identical substituents, CH2X. Now this one will be a little bit harder to see. So let's try to take this structure on the right and let's try to rotate it so that we can overlay it and superimpose it with our structure on the left. So we want this blue substituent. We want this blue substituent Y to be on the right, okay? So we're going to take our blue substituent Y and we're going to put it on the right by rotating our bottom substituents, our bottom 3 substituents. We're going to rotate them clockwise, like turning a steering wheel. So then, from this perspective, our red substituent X is unchanged in position. We didn't rotate our substituent X. Our blue substituent Y, after it's rotated, it's now in the back in the position that substituent 2 occupied. We have a hydrogen in the front and another hydrogen pointing to the left. And if we compare our structure and its mirror image, we see that these 2 mirror images are identical. So these 2 carbon centers are not stereocenters. And the reason for that is if we compare the structure and its mirror image, the mirror image is imposable. We do not have a set of enantiomers in this case. We always need 4 different substituents. So let's take a look. As we've established before, let's just do it one more time for practice. We compare these 2 structures. Our goal is to rotate one of our enantiomers and then try to superimpose our 2 structures. So we want our green substituent. We want our green substituent on the left. So let's rotate all of our bottom 3 substituents. Let's rotate it counterclockwise. And if we rotate it counterclockwise just 1 turn, we'd end up with our green substituent on the left, our red substituent is unchanged, it's still on top. Our blue substituent is now in the front, pointing towards us, and our yellow substituent is in the back, pointing away from us. And no matter how hard we try, to overlay these 2 structures, they are non-superimposable. The yellow substituent and the blue substituent are in different relative positions in these 2 structures. So in this case, this carbon is a stereocenter. And this pair of molecules are what we call enantiomers. Molecules that are non-superimposable mirror images that have different configurations at each of their stereocenters, to be more technical about it. Okay, so let's now move on and let's try some practice here. And let's focus on the mechanics of rotating molecules, rotating substituents to compare different species and determine whether or not two structures are enantiomers or identical molecules. So one of the most common methods of rotation that we have discussed previously is if you have any set of three substituents, so any set of three substituents in the same relative plane, you can rotate those substituents either clockwise or counterclockwise. So let's suppose we're comparing structures A and B. And one great tool that I'd use for practice is if you just input the structure into Marvin Sketch, it will assign the stereochemistry as R or S. And if they have the same stereochemistry at each center, then they're identical. If they have different stereochemistries at all of their centers, then they're enantiomers. So Marvin Sketch is a wonderful structure drawing platform that also allows you to check your work. And that's what I use a lot of the time to make sure that my test questions are on the right track. And when I was a student, that's how I often practiced assigning R and S configurations when I ran out of book problems. Okay, so when we take these bottom three substituents and we rotate them clockwise, in effect, we're exchanging the position of each of these substituents in our line, wedge, and dash framework. Okay, so if we move each of our substituents one position over clockwise, our fluorine is now going to end up in the dashed location. Our hydrogen is going to end up in the line location, and our chlorine is going to end up in the wedge location. So let's execute on that. Let's execute on that. Okay, perfect. So we're almost there. We're almost there. Now, in cases where your lines are arranged differently in 3D space. So notice how for structure B, our lines are pointing left. Well, in structure A, our lines are pointing right. So one trick to fix that issue is we're going to change our relative perspective. And we're going to try to look at it in a way where, so currently our fluorine is pointing back and our chlorine is pointing towards us. So if we draw like a piece of paper here, we have our bromine. We have our hydrogen. Our chlorine is pointing out. Our fluorine is pointing in. Okay. Now, we are looking at this structure from the front. Now, all we have to do to change our relative position of substituents is to look at it from the back perspective. Okay. So in this case, so looking at it from the back perspective, we have our bromine pointing up still. Our fluorine is pointing out of the page. To the right. Our chlorine is pointing into the page to the right, and our hydrogen is in the plane of the page, pointing on the left-hand side. Now all we have to do is rotate our substituents counterclockwise, and we end up with the following relative arrangement of substituents. We have our bromine pointing up, our chlorine pointing to the left, our fluorine pointing in the back, and our hydrogen pointing out of the page. So if we compare structure A, and structure B, we notice that the relative position of our hydrogens and fluorines are different. So these two structures are enantiomers. So just to refresh once again, just to show you this method once again. So let's suppose we have our structure. We have bromine, chlorine, fluorine pointing out of the plane of the page, and hydrogen pointing in. My first step is I draw my flat piece of paper, draw my bromine, chlorine, my fluorine pointing out, my hydrogen pointing in. Now, we're currently looking at it from the front, right? And a quick way to change the relative position of your line substituents is just to pretend like you're looking at your structure from the back. Okay? So when we look at our structure from the back, essentially what we're doing is so if we're viewing the structure from the back, let's now map on each of our substituents. So viewing our structure from the back, our bromine is still pointing up. Now all of our substituents that were originally on the right are now going to be on the left. So our chlorine is now on the left. Additionally, any substituents that were pointing into the plane of the page are now pointing out of the plane of the page. So this hydrogen, so it's in the back left. The hydrogen is now in the front right position. Likewise, the fluorine is in the front left. The fluorine is now in the back right. And this is easy to see with a model. If you just physically place the model down and just walk to the other side of it, you'll see that from this perspective, you now have your line substituents pointing in the same direction, and you've correctly adjusted the dash wedge notation of your other substituents. I really encourage you to break out your model kits when you're going through each of these common types of rotation, as this is a skill that you'll be able to use your model kits on the exam. So it's important to be familiar with your model kits and then slowly develop this spatial reasoning skill. Let's look at a few other types of rotation. But before we do that, let's discuss this idea of the plane of symmetry. So molecules that have a plane of symmetry, it's a vertical or horizontal plane that divides the entire molecule into two pieces that are exact mirror images. And molecules that contain a plane of symmetry are achiral. So a plane of symmetry, once again, is a vertical or horizontal axis that results in identical substituents on both sides of the axis. So if you observe an axis of symmetry, then the molecule is achiral. So, for example, in the following structure, we can draw a vertical axis of symmetry, and on the left and on the right, we see we have a CH2 and a CH2 on the left. We have a CH2 and a CH2 on the right. So this center and this molecule is achiral. Remember when we brought up this idea that attached to each carbon, we must have a total of 4 unique substituents. So in this case, it's as if we have these alkyl chains that are identical. The bromine pointing out of the plane of the page and a hydrogen pointing in. Since our substituents are identical, this center is achiral. It's not a chiral center. You have to have 4 unique substituents. Now, let's take a look at this example here. In this case, we have 2 identical hydrogens, and we can very easily see an axis of symmetry if we think about what happens if we intersect. So let's pretend this bromine and chlorine are in the same plane. And as we see, on one side of our plane of symmetry, we have a hydrogen. On the other side, we have another hydrogen. So we have identical substituents. On both sides of our plane of symmetry. So as a result, this molecule is achiral. Now you do have to get a little bit creative with how you pick your planes of symmetry. And in some cases, you may just have to split your molecule straight down the middle. For example, in this structure here, let's fill in some information. So if we look at our substituents, and just one side note, you are going to have to make sure that both of your substituents have the identical stereochemistry as well. And we'll talk about this in more detail when we discuss meso compounds. But in this case, we can divide this structure straight down the middle, and we have a plane of symmetry. We'll discuss these types of molecules and how stereochemistry can impact whether or not there's a true plane of symmetry. You want to make sure that we have the same stereochemistry on both substituents. Otherwise, the substituents aren't exactly identical. So for example, looking at the following molecule, if both of these alcohols were pointing up, we can draw an axis of symmetry, and we say that both of these substituents are identical. They have the same stereochemistry, so these substituents are identical. And as a result, because this molecule has an axis of symmetry, this molecule is achiral. So we have identical stereochemistry, we have an axis of symmetry, and as a result, this overall molecule is achiral. So you do have to pay attention to the stereochemistry when deciding whether or not an axis of symmetry is present. Okay, so let's discuss chiral centers in detail. We've been using the definition of a chiral center as a point in a molecule where there are 4 different groups or atoms attached to a carbon. So for example, 5-bromodecane is chiral because we have a total of 4 different substituents attached to that carbon. Now, if 2 substituents on a carbon are the same, if there is an axis of symmetry, the carbon is achiral. So, for example, if we're looking at chiral centers, and this is where I really encourage you to draw out your hydrogens. So this carbon attached to the chlorine has 4 different substituents. And as a result is a chiral carbon. And we designate chiral carbons with a little asterisk. Now, if we compare the carbon attached to the chlorine to this isopropyl-like carbon, my question to all of you is, let's dissect now what substituents are attached to this isopropyl carbon. So first we have a methyl, we have another methyl, we have a hydrogen, and we have the rest of our chain. Now, as we see, these two methyls are identical. So this center here is a chiral. It's not a chiral center. Well, let's just say it's not chiral. Okay, so you really have to pay attention to your substituents on each carbon if you're identifying chiral centers. So let's take a look at the following molecule. And let's try to identify our chiral centers. So the first thing I'm going to do is I'm going to draw out my hydrogens. And now we're going to look for every carbon with 4 different substituents. So we see here we have an amine, a carboxylic acid, a hydrogen, and an ester. So 4 different substituents. So that's our first chiral center. Focusing on this ester carbon shown here, we have an alcohol. So that's 1 substituent. We have a hydrogen. We have an ethyl group. And we have a methyl group. So we have 4 different substituents. So we have a total of 2 chiral centers in this molecule. Perfect. So again, when you're looking to identify chiral centers, you look for any carbon with 4 unique substituents, assuming there's no axis of symmetry present. Always be on the lookout for axis of symmetry and for potential achiral compounds containing chiral centers. So when we think about chirality centers or chiral centers in chiral molecules, groups are considered different if there is any structural variation. So if the groups could not be superimposed. So for example, let's take a look at some cyclic molecules. So for cyclic molecules, we compare looking at each direction in the ring. So you count your carbons clockwise, you count your carbons counterclockwise. And for cyclic molecules, if they have the same groups with the same number, with both your counterclockwise and clockwise counting method, then your molecule is achiral. So for example, let's take a look at the following center. Let's take a look at the following methyl cyclohexane system. So counting clockwise, we have 1, 2, 3, 4, 5, 6. So our methyl is at carbon number 1. And at carbon number 2, we have a CH2. At carbon number 6, we have a CH2. Let's now count in the opposite direction. So let's count counterclockwise. So 1, 2, 3, 4, 5, 6. So as we notice, if we compare and we look at carbon 2 in both of our counting methods, our substituents are identical. And as a result, we can clearly see that we have an axis of symmetry. And as a result, this methyl cyclohexane molecule is achiral. So let's try this counting method one more time just to make sure. So counting 1, 2, 3, 4, 5, 6. So that's clockwise, and then counterclockwise, 1, 2, 3, 4, 5, 6. Now, as we see, if we compare our carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6, we have the exact same substituents. At all of these carbons, the only substituents we have are carbon with 2 hydrogens attached, right? So at all of these carbons, we see a carbon with 2 hydrogens attached. So no matter whether we count clockwise or counterclockwise, our substituents are identical. And as a result, we can clearly see there's a vertical axis of symmetry dividing our molecule. Now, if we compare this to 2-methyl cyclohexanone, let's try our exact same counting method. So clockwise, 1, 2, 3, 4, 5, 6. And then counterclockwise, 1, 2, 3, 4, 5, 6. So let's compare carbon number 2 and carbon number 6. Okay, so let's look at carbon number 2. So at carbon number 2 in our first counting method, we have a ketone. In our second counting method, we have a carbon with 2 hydrogens attached. As we can clearly see, these substituents are different at carbon 2 in both of our counting methods. And as a result, we can clearly see that there is no axis of symmetry. There is no plane that we can divide our molecule that would give us a perfectly identical substituents on both sides of the plane. So, as we can see, if we look at our stereogenic carbon, it has a total of 4 different substituents. It has a hydrogen, has a methyl, has a long alkyl chain, and it has a ketone functional group. So this center is a stereocenter, and this molecule is chiral. So this counting method is just a standardized way of checking for axis of symmetry when you're dealing with a cyclic molecule. Now, let's try some practice examples, and let's try to label the chiral centers in each of the following molecules. Now, I'll start us off. I'll do a few examples, and then you'll handle the next pair of examples. So just like always, I'm going to draw out each of my implied hydrogens. This really helps me see if I have 4 different substituents. So looking first at this benzylic carbon, we have 1, 2, 3, 4 different substituents, and I can't see any symmetry plane or axis of symmetry. So this first center is a stereocenter. Additionally, this adjacent ether carbon has a hydrogen, a unique alkyl chain, another unique chain, and an oxygen attached, so 4 different substituents. So this adjacent carbon is also a chiral center. And finally, the carbon attached to the amine, we can clearly count 1, 2, 3, 4 different substituents, so that's also a chiral center. So this molecule has a total of 3 chiral centers. Looking at the next example, this example is slightly ambiguous in that we need to know the stereochemistry, but if we draw out our implied hydrogens, we see that this center does indeed have 4 different substituents. However, this molecule has a plane of symmetry, and depending on the stereochemistry of each of these chlorines, this molecule could be achiral. So always just be on the lookout for a plane of symmetry. And if you have identical stereochemistry on both sides of the plane of symmetry, then the molecule itself is achiral. Now, let's have you spend some time working on these next few examples, and I'd like you to identify all of the chiral centers in the following 2 molecules. So please pause the video at this time, and then we'll resume to discuss in about 2 minutes. Okay, so I'm going to get started now. So first and foremost, I'm going to draw out all of my implied hydrogens. And now as we can see, looking at this first carbon, we have 1, 2, 3, 4 unique substituents. We have our first chiral center. Looking at our second carbon, we have 1, 2, 3, 4 unique substituents. We have our second chiral center. This second example is a little bit tricky. So starting off, looking at this alcohol carbon. So we have an OH, that's 1 unique substituent. We have a methyl, and then we have another methyl. So because we have 2 identical substituents, this center is not a chiral center. Comparatively, the carbon attached to the chlorine has a methyl, an ethyl, this complicated alkyl chain and a chlorine. So 1, 2, 3, 4 unique substituents. So we do in fact have a chiral center in this molecule, and that's on the carbon attached to the chlorine. So always just remember a chiral center, we have 4 unique substituents, and there's no axis of symmetry present in our molecule. Okay, so let's keep going now and let's talk about drawing enantiomers. So enantiomers are a pair of molecules that are non-superimposable mirror images. Enantiomers have the opposite configuration at every chiral center stereocenter. So the trick for drawing enantiomers is first you draw your molecule, and for the second step, you're going to draw a mirror plane, which is essentially an axis that you're going to reflect your molecule across. It can either be behind your molecule, under your molecule, or to the right next to your molecule. And then all you do is you draw the mirror image of the molecule across this mirror plane. Okay, so let's talk about practically how each of these works. So for a mirror plane behind your molecule, so this square is going to be our mirror that we're going to reflect our molecule across of. So we're going to draw out our implied hydrogens, okay? And considering our methyl is dashed, our hydrogen will have the wedge. So we're looking at it from the front. And just like we did in our exercise where we changed our perspective, we're going to look at, and we're essentially going to reflect our molecule through this mirror plane. So all of our substituents that are originally in front are going to end up in the back. So let's take a moment to try this. Let's take a moment to try this. So we have our hydrogen originally in front and our methyl groups in black. Once we reflect it about the mirror plane, we end up with our methyl in front and our hydrogen in the back. One key feature is, do you notice how our phenyl group is in the same relative position? So you only invert the dash wedge notation for each stereocenter. Otherwise, you draw your molecule in the exact same way. So let's look at an example here. We have our hydrogen with the wedge and our methyl with the dash. And again, if we're inverting all of our stereocenters, we now have our methyl in front and with a wedge and our hydrogen in back with a dash. Now, let's try together now to draw, let's try to draw a mirror image of each of these two molecules. Let's try to draw some mirror images now. Oh, sorry. So we're going to now look at the bottom pair of molecules, and we're going to reflect each of these molecules about their mirror plane. So here's our mirror plane behind our molecule, and we're going to draw the enantiomer of each of these two molecules. So first, let's draw out our implied hydrogens. And for a mirror plane behind our molecule, we're just going to invert every stereocenter. So I'm going to draw my alkyl chain exactly as normal. And now our hydrogen, which was originally had a wedge, it's now going to receive a dash. Our amine, which originally had a dash, is now going to get a wedge. Our alcohol, which had a wedge, is now going to get a dash. And our hydrogen, which has a dash, is now going to get a wedge. Perfect. So we just inverted the stereochemistry at each of our stereocenters, keeping all of our other substituents in exactly the same relative orientation. Okay, let's try to now draw the enantiomer of the molecule on the right. So just like before, we keep our alkyl chain consistent. Our hydrogen has a wedge. We're going to invert it to a dash. Our amine, which had a dash, now gets a wedge. Our oxygen, which has a wedge, now gets a dash. Our hydrogen, which has a dash, now gets a wedge. Everything else stays the same. So the only difference between the structure on the left and the structure on the right is I just drew out our implied hydrogens. So if we compare these two sets of molecules that are mirror images of each other, these two sets of molecules are enantiomers. They're identical in connectivity, but they have a different stereochemistry at each of their stereocenters. Let's keep going with other methods of drawing enantiomers. And it's really important to recognize all the different ways that you can draw enantiomers, because when I show you a pair of molecules, it's really important to be able to identify quickly whether they're identical molecules or whether they're enantiomers. So one other way to draw enantiomers is to visualize a mirror plane below your molecule. So you're going to invert your molecule vertically, and you're going to retain the exact same dash wedge notation. So all you're doing is you're going to flip your molecule vertically 180 degrees. And you're going to make sure that the dash wedge notation stays exactly the same. Okay. So to help you visualize a little bit and to help you see that, and what we're really going to show is we're going to show that these two structures, so this is the structure after inversion, and this is the structure before inversion, and we're going to show that these two structures are indeed enantiomers, that they're non-superimposable mirror images. So if you first rotate your carbon-carbon bond to move this benzyl group towards the bottom. We're next going to rotate our substituents on the stereogenic carbon, and we're going to exchange the relative position of our substituents. So in this rotation, what we're doing is we're essentially changing the perspective that we're viewing this molecule from, and we're going to set it up so that this amine, instead of being pointing towards us in the line, is pointing away from us in the line. And to do that, we're going to rotate this entire structure. I guess you can say, looking at it from this perspective, we're rotating it counterclockwise. So after rotation, so that this amine, instead of being in a line pointing towards us, is pointing away from us, we now have our hydrogen pointing towards us, our methyl pointing away from us. And if we compare it to our above structure before this inversion, so if we compare it to our enantiomer, we see that our methyl and hydrogen are in different positions. Again, I really encourage you to build the model and try each of the rotation steps that I've outlined. We'll be doing more work with model kits in the laboratory as well as in the homework assignments. Let's now practice on our own drawing out enantiomers using this bottom mirror plane. So we're just going to reflect our entire molecule 180 degrees, keeping our dash wedge notation identical. So for the following molecule, so I'm going to draw the vertical mirror image. So I'm just inverting my molecule 180 degrees, keeping my dash wedge assignment exactly identical. It's really important that when you're drawing enantiomers, you do not change the dash wedge notation. Now, to show that in fact that these two molecules are enantiomers, let's take a moment and let's just subject instead of subjecting this molecule to just rotation, all we have to do is just change our view perspective. So again, just like before, we're currently, if we think about it from the perspective of planes, we're currently viewing our molecule from the front. Now, if we want to adjust the orientation of our molecule, what we're simply going to do, if we pretend that we have a flat mirror plane, is we're going to rotate all of our substituents 180 degrees. So we're essentially going to flip the entire molecule by 180 degrees. And we're going to look and see what happens to each of our substituents. So when we flip each of our substituents 180 degrees, all of our wedge substituents will become dashed, and all of our dashed substituents will become wedged. So then after we flip each of our substituents 180 degrees, we'll end up with the following structure. And as we can see, if we compare this structure to our enantiomer, we can see that these two structures are identical, except they have the opposite configuration at every stereocenter. So these two structures here are enantiomers. Okay, let's now cover the last major mirror plane method, which is a mirror plane next to your molecule. So you're going to invert your molecule horizontally, but you're going to retain the same wedge dash notation. So this is for drawing enantiomers. So we draw all of our wedges and dashes the same, except we flip our molecule horizontally 180 degrees. So just really to help you see and to help you visualize the fact that these two molecules are enantiomers, let's try some rotation, and let's try to rotate our molecule in order to directly superimpose these two structures. So the way this works is you're going to take your mirror image shown up here. This is our mirror image that we obtained via reflection. And we are going to rotate it 180 degrees horizontally. So after we do that, we have our phenyl group on the left, and we have our amine on the right. We are going to rotate our phenyl group, so it's now pointing down. And then we're going to rotate the substituents on the carbon attached to the amine. So that the amine, instead of pointing the line towards us, is pointing in the line away from us. And the quickest way to do that is just to, when you draw your amine pointing away from you, you change this dashed hydrogen to a wedge, and this wedged methyl to a dashed. So after rotation, you'll end up with the following structure. And as we can see, if we compare the arrangement of substituents on our stereocenter, that our substituents have the exact opposite stereochemistry at each of our stereocenters. So these two structures are in fact enantiomers. So let's now try drawing the enantiomer of the following molecule. So again, if we're using a horizontal mirror plane, you're going to draw your molecule reflected 180 degrees. So you're going to draw the exact horizontal mirror image, keeping the dash wedge notation the same. That would look something like this. Okay, so let's now pause today's lecture and we'll pick up next session discussing stereoisomers, optical activity, and how we can identify compounds as optically active and how chirality is related to optical activity.